ok, ok. Sì, sì, io seguo lì, però è un attimo complicato. Ah, ok. Okay. Thank you, guys. I'm Andrea Ferretti. I work in the research and development group here in WeCredit. And I'm here to present something about how to make good use of the Scala type system to enforce some stronger invariants. One thing, here there is a big wall of text. You do not have to read it. This is just for when the slides will be published on the site so that people will be able to run this iScala notebook on their own. But mainly the code, you will have to read it, but you can disregard what's written in the wall text. So don't bother if it's a little small. So what I want to tell you. First, I'm not an expert on type systems, so it will not be a theoretical talk. But the whole point of dependent type system is to have a language of types that is in some sort be able to depend on the language of values, so that you can define types that are more precise. A typical instance would be, say you want to avoid the division by zero error. So you would like to have a type that contains all integers, say that are not zero. So that if you get such a number, you know you can divide by it. But other than zero, you could have a type for a number different than 5 or whatever. So there's just no way to have in many type systems such a type, because the type depends on the value 0 or 5. Or there are other kinds of operations that you may want to enforce. Say you want to zip two lists. You would like to be able to guarantee that the lists have the same length. But the length is not encoded in the type of the list, usually. Or you may want to do modular arithmetic. But you would like to avoid summing an integer modulo 7 to an integer modulo 13. And again, you want the type system to prevent you at compile time from doing this stuff. So this is something that can be done in dependently typed languages. And, well, something can be done also in Scala. And probably many of you already, some of you already know Shapeless. That is an exploration on these ideas. I won't use Shapeless today. But I will show you how some of this stuff is actually implemented from scratch. So what I will try to do is first something about implicits that we will use later, then an introduction on type-level computations, and then some applications. And in particular, I will be able to show some poster childs of dependent typed languages, such as fixed-site sequences, modular arithmetic, or balanced trees. So, Scala in itself is not a dependently typed language, but has some features that can be put to good use to do this. In particular, there are type members for objects, and two such types are equal if they are the same type on the same object. So, in some sense, types can depend on values. And this is one thing that we will use. And another thing that we will use is the implicits. One can do everything without implicits, but it gets very messy very easily. So I will start with some remark on implicits. Okay, first we want to be able to recognize an implicit of a given type. So we need a function, polymorphic, that given a type, it gives us the unique implicits of the type, if there is one. Otherwise, it's a compile time error. And this is, well, the first thing that we will present are all in the standard library of Scala. I just present them to show that there's nothing magic about that. You could implement them. So implicitly is a function that takes an implicit value of type A, and it gives you that A, if there is one. So just to check that this is working, okay, just to check that this is working, I define a type, foo, and an implicit value of type foo, which is foo of 5. And I run the function implicitly of foo, and this will catch the implicit, and that's foo of 5. Okay, why do I need this? I need this to recognize whether two types are the same. So what is the trick to find out if two types are the same? Well, I will use implicit. So I will ask the compiler to provide me implicit that prove that two types are the same, and no other implicit. So I define a type here, which is equal colon equal, that depends on two types, A and B. And I will provide the implicit instances of this type for A and A, but I will not provide instances of this type when A is different from B. So doing this, I can check whether int is equal to int. This notation is just the infix notation for generics. So this will compile because int is equal to int, so the compiler is able to find an instance of equal colon equal int int. But if I were to, well, now this is a little difficult to do here. If I were to do this will not compile, because the compiler is not able to prove that int is the same as string. So since this is a little inconvenient, because, well, we do not want to have compile time errors. We'd like to check if something is equal to something else and get true or false. That's more convenient. Well, there's a little trick for this. I can just define a function, type equal equal, AB, and it will ask for an implicit evidence that A is equal to B, but I will give it a default value of null. So if A is not equal to B, this will compile in any case, but the value will be null. So I just can check whether the value that I get is or is not null. So this is a more convenient function, and with this I can check that int is equal to int. So this is true, but okay, int is not equal to string. Okay. Then I can do the same for subtyping. Not that I will use it, but the same can be done with subtyping. The only difference is that in this generic type, I make A contravariant and B covariant. So I provide an instance of this generic type for A and A, but it will be valid as an instance of A and B whenever A is a subtype of B. So at the same time, I can check that list of int is a subtype of sec of int, because this compiles. And if I were to check whether int is a subtype of string, this will not compile. Okay, this is fine. And then I can, as before, transform this into a function that gives me true or false, which is more convenient. So int is not a subtype of string, but list of string is a subtype of sec of string. Okay, this is just some preliminary because, well, we will work with types and we need to be able to tell whether they are the same or not, and this is a convenient way to do this. So the next thing I would like to do is to encode some usual values as types. So I will start from booleans. There are just two booleans, which are true and false. So to encode these, I will use some traits. And I will define a trait bool and two traits, which I call true and false, that extend bool. So I will interpret this as saying that true and false are bool in some sense. And I will never instantiate this stuff. This stuff is just to make type-level computation. And we will not get instances of these traits. So this is a start, but we do not have any operation. We have Boolean operation that we want to be able to define. So the next thing is to define, for instance, the simplest of the Boolean operation, which is not. And of course, I can leave it abstract on bool, and define it with a type member. And then I can see that for the trait true, the value of not is false, and for the trait false, the value of not is true. So this works, and I can check that false hash not is the same as true, just to make sure that everything is clear. This, well, is just an issue with the notebook. It's not it looks like a comment, but it's just the syntax to access a type member. So it's like false dot not in the value world. And I can check that this is the same as true. And, well, it works, it's true. So we can do something more complicated and do the if operation. So what is if? Well, whenever I have an if, I have a Boolean. And based on the value of the Boolean, I want to take one of two branches. So I will define a type if, which is a type member, and it depends on some type parameters. T will be the type that represents the true branch. F will be the type that represents the false branch. And then there is this up. Up is just to make this type. So up will be the type of the value. We do not have a language of types. So what we have done for Booleans is encode true and false as subtype of bool. So we ask T and F, whatever they are, to be subtypes of up for some parameter up. And the result of the if operation will be something of type up. And then we specialize the definition. So when we define this for the true type, we define if to be equal to T, and we specialize for the false value to be equal to F. Okay. And then, well, just some syntactic sugar to make this more palatable. So first we do not need not at all, because not can be defined in terms of if. And then we can define some more functions like AND or OR on Booleans. So here in this object, I define a few operations. These are as well types that depend on some type parameters, and I interpret them as functions that of this and this type, and the result will be this type in some sense. Okay? So how I do define not, which is the simplest? Well, the result of not will be a bool. So it will be a hash. Well, the third parameter here is bool because the result is a bool. And to negate a value, well, if A is true, it has to return false, and if A is false, it has to return true. So I just invert. F is true and T is false. And similarly, I can define operations with more than one parameter, like AND or OR. And these are defined, well, AND is defined, well, I look at the value of A, and if A is true, well, then the value of the AND with another Boolean is the value of B. But if A is false, I'm certain that the result is false. And similarly for OR. Okay, so I've defined it. I import these types, and I can check that, for instance, true is the same as not false. And this is true. This works. And I can make a couple other checks, like false is the same as true and false, and true is the same as true or false. Okay, so this compiles, so this means that these equations are true. So again, it's a little inconvenient to work always with types, so I want to convert them to values. So I will define a polymorphic function, bool to val, will take an A, which is a bool, so it will be either true or false, and it will return a Boolean, so an actual Boolean value. And, well, the naive way to do this will be, okay, I just check if the type A is true. But, well, this does not work. The reason why this does not work is that this function here, type equal equal, had an implicit parameter if, which was of type A equals true. But the implicit parameter resolution happens when this is defined. And at this point, there's nothing that says that A is the same as true. So I need to thread the implicit parameter. So I will ask for an implicit even here so that it gets passed to the type equal equal function. And when I do this, I can check that, well, bool to val of true is the Boolean true, and bool to val of true is the Boolean false. Okay, that's it with Booleans. Next thing we want to encode are natural numbers. And these are slightly more complicated because, well, we use the Peano encoding. In a sense, a natural number is either 0 or the successor of a natural number. So we define a type with a trait, and we call it nat. And we define 0, which is a given trait that is nat. And then we define a function successor. So it's, again, a type, but it's a generic type, and it has a parameter n, which is a nat, and the successor of n will be another nat. This is what we are saying, but saying the successor of n, which is nat, extends nat. And then we can define, we can give type aliases to the successor of 0. For instance, I can call it 1. And so on. Okay, this is just like when we started encoding Booleans, but we need something more. We need some operations. So I can just copy if and do something like if 0 to distinguish two branches based whether I'm on the 0 case or on the non-zero case. This is just the same as if. It's defined exactly the same. And I can check that, for instance, if I do if 0 on 0, and I say if 0 take the true branch, otherwise the false branch, well, I want to be sure that the result is the true branch, because 0 is 0. So this works. Okay. And we can define more functions. The next function we can define is the predecessor of a number. Now, of course, here you see the functions that we define are total. So the predecessor of 0 would be -1, which is not in our range. So we will adjust the define of predecessor so that the predecessor of 0 is 0, because otherwise we cannot encode this. And so I can define another type, pred, on nat, and that's that the predecessor of 0 is 0, but the predecessor of, on the successor of n is n. And, well, I have to define 1 again because I have overwritten the previous definitions. And I also transform this type member into a function. It's like defining a function from a method, which is just more convenient, so I have to avoid all these hashes. So this works, and I can check that, for instance, the predecessor of 1 is 0. Okay, and it's not the case that 1 is the predecessor of 0. So this is false. Okay, well, I will start to make some more interesting operations like plus. Now, I would like to define something like this, but it does not work. The reason it does not work, well, first what I was trying to define. The plus of A and B, well, one would think, well, I go on A and check if it is 0. If it is 0, I just return B. And if it is non-zero, I take the predecessor of A recursively. I do plus of this and B, and then I take the successor. The reason this does not work is that I'm defining the type plus in terms of the type plus, which is not something that the Scala type system will allow. But I can do this if I encode plus as a type member on our naturals. The reason why I can do this is that when I do this, so on the successor of n, I define plus with some b by taking n plus b and taking the successor. And the reason I can do this is that I'm defining the type plus on the object subs of n in terms of the type plus on the type n. And since these types are distinct because they are on different objects, and Scala has objects that depend on types that depends on objects, so these values are distinct and there is no cyclic reference here. So this is well defined. And again, I transform A hash plus B in plus AB, which is more convenient to write. And I define some more types like 0, 1, 2, 3, and 4. So I can check that 2 plus 2 does make 4. So the compiler proves for us that 2 plus 2 is 4. And if we ask the compiler to prove for us that 2 plus 2 is 3, it says it's false. So this is fine. And we do the same as before. And we try to convert this stuff into actual numbers. So it's slightly more complicated because we do not have just two types like true and false. So in order to do this, we introduce some other type. I call it not converter. it has both a type parameter of type nat and a value of type int. And I will create instances of this nat converter only when the big N is equal to the little n. So I define a zero converter, which has type 0 and value 0. And I define a function that produces more converters. So given some converter for n, I define the converter for n plus 1 by putting as type the successor of n and as value n plus 1. And then I can use this to define a function net to value. It takes an implicit converter and returns just the value that is in this class. So I can check that the type 2 gets converted to the number 2. Okay, and then I can add multiplication and factorial and GCD and a lot of operations on natural numbers. But it's a little inconvenient because to add plus, I had to reopen my definition and add plus as a type member. So I don't want to do this for each and every function that I define. So I would like to give a general recipe to do inductive definitions. And to do this, I will mimic what we do for a fold on a collection. So in the type world, a fold is something that takes a function from an A and a B and returns a B. So it can be encoded by a trait that looks like this. So a trait that depends on two types, A and B, and there's a method applied that takes an A and B and returns a B. So what is the analog in the type level world of this stuff? Well, it is a trait, again, fold, AB, which has a type applied that depends on some X, which is a subtype of A, and Y, which is a subtype of B, and returns something which is a subtype of B. Given these, well, I can finally define a general way to do recursion. So how do I do recursion? Well, I will define type, which I call fold_r on nat. And fold_r will need some initial value, which I call, initial type, sorry, which I call init. And then I will need an operation. An operation will be a fold that takes the current natural and the accumulator, which is of type up, and returns the next value of the accumulator. And so it's a fold of nat and up. And okay, again, up is a type parameter just there to make the thing type. And what it returns is something of type up. So this is general form to define something that starts from init of type up, and then at each step takes the current value of the accumulator, the natural number, and returns something else, the next value of the accumulator. And then I can implement this. On 0, I just return the init. And on the successor of n, what I do is I do the fold on n with the same init and op. And when I've done with the fold on n, I apply my operation on the accumulator so far and the number, which is the current number, which is the successor of n. So this, well, is the most complex thing that is in this talk. So once I do this, I can define a few operations like plus. Plus is just a recursive definition. Well, the operation that you do is just incrementing the accumulator. And, well, I have to redefine all my conversions because I've redefined the naturals once again. And I have to redefine all the type aliases. But when I've done this, I can check that 3 plus 4 says 7. Okay. And then I can implement more operations like this. So other than plus, I can implement, say, times. So A times B, it's a recursive operation on A, and at each step, I sum B. So I define an operation which is sum of B, which returns the sum of the accumulator in B. And this is my recursive operation. And I can do a decrease operation, and I can use this to do minus. Of course, minus will be a bounded minus. So if I do 12 minus 5 is 7, but if I do 7 minus 9 is 0, because I do not have minus 2. And, well, with these operations, I can combine them. I can check that 2 times 3 plus 2 is 8. and 5 minus 3 is 2, or 3 minus 5 is 0, because I said it's bounded. Okay, and I can define more natural operations. I don't want to spend much time on this, but it's the same stuff. I can define again if 0. I can define whether a number A is less or equal than a number B, because, well, I do A minus B, and I check whether this is 0. And less of A and B is defined, well, the successor of A has to be less or equal than B, which is the same thing. So with this, I can check that the if 0 operation works just as before. And I can check that if I take the predecessor of 3 and then the successor, I get 3 again. Okay, and then I can check that 3 is less or equal than 4, but it's not the case that 4 is less or equal than 3. Okay, so this is everything I wanted to say about type-level computations. We have encoded the Booleans with some operations on them, and we have encoded the natural numbers with some operations on them. And this is enough to give some applications of something which usually you find in independently typed languages such as Idris or Agda or Coq. You know, here we are a little more limited, because when we have a dependently typed language, usually there is an associated proof system, because say if I define the type of numbers that are non-zero, well, it may be the case that it's difficult to prove, for the compiler to prove that a number is not 0. Maybe the number is of the form x squared plus 1, so it will not be 0, but the compiler is not able to prove this. So we need to be able to give proofs to the compiler. And we can sort of do this in Scala, but it's not that convenient. But still, we are able to give some examples. So I will give the most typical example. I will start from fixed length lists. So lists that encode in their type how long they are. So I will start actually from normal lists. This is the usual definition of lists. It's straight, say. It has a head and a tail, and it has two implementations. There's an empty list and the cons. The problem is that on the empty list, these operations like head or tail have to give errors. Or they can be undefined, but then they will not be defined on list, only on cons, and this gets messy. So this is our define in Scala anyway. So Neil has the operation head and tail, but they give exceptions. And this, well, we can use them as usual. I define a list, 1, 2, 3, 4, and I can take the tail, which is again a cons. So the naive idea would be, okay, let us have some n lists, say, which encode their length as a type member. And the naive definition would be like this. So the empty list does not have the head and tail operations because they are unsafe. And these are defined only on n cons. And the n is there to encode the length of the list. And this seems to work at first. I can define a list of length, which is an cons of a tail of length 2, so it's a list of length 3. And I can take its tail, but the problem is that as soon as I take the tail, because the tail of a cons in general is a list, it's not another cons, because I could eventually get to the empty list. So the type of the tail is actually list, not cons. So the compiler does not know that since the length is enough, I can keep taking the tail. So if I do nlist.tail.tail, this will not compile because nlist.tail is just a list, it's not a cons. So it's not that good, this definition. And I can try to define some more complex operations like append. So I would like to say that when I append a list of length m with a list of length n, I get a list of length m plus m. And I give the naive definition. But, well, the compiler is not able to prove that this recursive definition will actually give me a list of length m plus n. So what do? I cheat. I cheat and I say, okay, compiler, trust me. I will just write a wrapper for lists, for unsafe lists. So a wrapper for lists which do not know their length, and the wrapper does know the length. And I will define all the operations on the wrapper so that they are safe. So the compiler does not have to get in the way. So I define something like sized, which depends on two type parameters. A is the type of the content, and N is the length. And it takes an underlying sequence. And, okay, this will be a wrapper. And I want to be able to evaluate this sequence on a natural, so not on a number. So I want, if I need the first element, I evaluate this sequence on the type 1. So this is why I define apply here on this wrapper, which takes an m, which is the position of the value that I want to have in the sequence. And I say, okay, but this operation will compile only if I have an implicit that tells me that m is less than n. And if this is the case, I also ask for an implicit to convert m to a value. And then I convert m to a value with not to value, and I take that value in the underlying sequence. So this sort of works. I can define the sequence of size 3 that wraps a list 1 to 3, and take its first element, giving it the type 1. But still, well, if I give it the type 4, it does not compile, because the compiler is not able to prove that 4 is less or equal than 3. But still, we have issues, because there is nothing that prevents me, for instance, to define a list of size 8 whose underlying sequence is actually of length 3. And so when I try to take the fifth element, I get an exception. Or reverse, I could use a smaller number here and a longer list, and this will not compile even though the list is long enough. So this is just a matter of putting some stuff private. So I don't want everyone to be able to construct this list as they want. I make the constructor private so that then the only way to construct this list is to use my method, and my method will return an option. So it will construct an instance only if the list is of the right length. So given this here, given this, I can do a size 3 list, and this I can extract it with pattern matching on sum. But if I try to do the same as before, I get none. So I have no instance of this sized sequence. And similarly, I cannot manually construct it with new because the constructor is private. So when I have this S, as before, I can get it the second value by giving it the type 2. And then I can extend this and add more operations, like adding an element to the end or to the beginning, or appending, or taking the head. And in each of these cases, I ask for the compiler for implicit that gives me the guarantee that what I'm doing is safe. So for instance, I can take the tail of this list, but only if 0 is less than n. So I cannot take the tail of the empty list, and so on. And I also define some more, the empty list of type A, or the list with just one element of type A, just for convenience. And given this, I can do like before, and I have this list of size 3, and I can add 5 and get a list of size 4. So the compiler keeps track of the length while I'm doing operations. I can concatenate S with itself and get a list of size 6. I can take the head or the tail. But if I take the tail of the tail of the tail of the tail, this will not compile. Okay. And this is just to show that if I use this other single version, I do not have to unwrap the option, or I can start from the empty list and do something like this. So it's almost as convenient as usual lists. So another example is something about modular arithmetic. So I want to perform operations modulo some number. So one way to do this is to encode a number, say 5 modulo 7, as the pair 5 and 7. But this has a few disadvantages. First, I will need double the space. So if I have 1 million of these numbers, I have 1 million of pairs, which are all boxed, and every one of those will have the number 7 in it, because they are all number modulo 7. I don't want to double the space that I need to encode this. And also, if I try to sum a number modulo 7 to a number modulo 5, well, I can only check on the pair that this is not well defined at runtime and fail with an exception, while I would like to fail at compile time. So this is just a convenience type. I can define a class mod, which depends on n, which is not, and it's a number modulo n. And what it does, it takes an integer, and it reduces modulo the value of this type n. So this is stored as a lazy val, and then each operation is defined in terms of this little n. So if I do this, I can say define 10 modulo 4 using 4 as a type. And well, you see it's 2 modulo 4. It's automatically reduced. So the toString takes the little n then, and so it's reduced when it gets into this container. And then when I do the operations, like a times a, it's 0 modulo 4. And well, since the operation is done in such a way that the number is reduced when it's created, I can keep doing operation without ever overflowing. So for instance, I can define the power of a number modulo n recursively. So x to the y, where y is an int and x is a number modulo n. And if I define b like 6 modulo 7, I can take its 1000 power without overflowing. And if I try to sum b to some like 3 modulo 5, this will just fail to compile. So I will leave this example out because it's, well, you will be able to see this, the slides will be, the notebook will be available on the site. The final example, because I have a few minutes, it's balanced trees. So I want to define a type of trees holding some values of type A, but in such a way that it's a compile time error to construct such a tree which is unbalanced. Now, of course, balanced binary trees. So now, of course, binary trees can be balanced only if the number of leaves is a power of 2. So we will allow the tree to be not perfectly balanced, but not too unbalanced. So we will ask for the left branch to be at least as high as the right branch, and not more than one more than the right branch. So you can have the left branch which is a little higher than the right branch, but just one step. So I can define such a type, and what do I do? Well, it's similar to the above. I take type 3, which takes values type t, and also holds a type member which encodes the height. And I have defined a leaf or a branch which holds a value of type t, and that has a left tree and a right tree. But now, what I do is that I define a method apply to construct branches given a left and a right tree. But when I do this, I ask for implicit evidence that the height of the right branch is less or equal than the height of the left branch, and the height of the left branch is less or equal than 1 plus the height of the right branch. So this will not compile unless the heights match, at least approximately. And of course, as before, I should also put the other way to construct such trees private. I do not bother here, but of course there are other ways to construct trees. I just have to make sure that no one of them is accessible. So the only way to construct such trees is by my method, and my method will only construct well-formed trees, which are balanced. And then I can give some example. Like I do a branch which has a 1 and 2 leaves, and another branch B2 which has a 2 and 2 leaves, B3 which has B1 on the left and a leaf on the right, and B4 that has B2 on the left and B1 on the right. And here I have written the height is n1, 1, 2, and 2. And this all works. So I can check that the height of B1 is, say, 1, the height of B2 is 2. And I can keep constructing more complex trees recursively. So I can take, say, B3 and B4 and make it to the branches of another tree, B5. But as soon as I try to construct a more an unbalanced tree, this will fail. So if I try to do branch with B1 and B3, this will fail because B3 is height 2 and B1 is height 1, and I asked for the left branch to be at least as high as the right one. And also I cannot take a B4, which is height 2 on the left, and a leaf on the right, because that is it's a step of 2, which is not allowed. This also does not compile. And also B5 and B1 does not compile because the heights are 3 and 1. So that's all I wanted to present. These are just some applications. There are more constructions that come from dependently typed language that can be ported using these ideas in Scala. One of those, I actually show it in the notebook. So when it will be available on the site after the conference, you can check it on your own. There I also use a feature, which is the fact that the return type of a method is also allowed to depend on a type, which is a type on a parameter. So the return type is not fixed on the method, but depends on the parameter that it's passed in. So this is one more feature that allows Scala to simulate what one can do in dependently typed language. And of course, if you want to explore some more of these ideas, the first thing you have to do is, well, there is this blog by Mark Hara, which is a blog series about these type-level computations. Then there is Shapeless, of course, the library of Miles Sabin, which has these definitions and more ideas on the same page. And then I have added a few other links, including a talk about well, doing something like logic computation, like Prolog in the type system of Scala. You can get as crazy as you want. But I hope to have been able to show that there is, I mean, some sanity in this, because if you see some of this talk, it seems very weird and very unnatural and something that a little crazy, but you can use it for day-to-day programming and have some convenient stuff like modular arithmetic or fixed length list or something much more down to earth. So that's it. So if anyone has questions, okay, you can launch the...
Yeah, do you want to?
No, you...
Okay. Who?
I play with that enough in the...
Perché ci sto qua?
No, just talk. Just talk.
Ah, ok. Non avevo capito. Okay, what you showed is pretty cool. I never thought to type system in these terms. But I'm very impressed on a side, but I cannot figure out myself doing this stuff in day-by-day code. Okay, the question is clear, I think.
Yeah, what I think is that, okay, in day-to-day programming you will not define piano numbers. I mean, this is just, when you learn the technique, you have some way to define functions that take types and return types. And so, well, you can define stuff that is definable in an inductive manner, like piano numbers or other constructions. And, well, you don't have to define them by yourself, but the techniques are just the same. So once you've learned them, it's not that difficult to reconstruct these or more complicated examples. I could have defined the factorial or the GCD, and after a while, it's everything that's the same. But apart from this, I mean, it's a toy. No one uses the factorial and the type system in real programming. But a few of these conveniences are available in existing libraries such as Shapeless. So you can report the benefits by just using, say, such data structures which have more precise guarantees on what you want to do if you need it. So you may have some use case for lists whose length is known at compile time, and so you are able to guarantee that you zip lists of the same length or something like that. Heterogeneous lists also are an example. So are lists that track their type. So it's like a cons list, but at each step you do not cons a new value on top of the tail, but also a new type. So you construct a new value and a new type at each step. So they can be heterogeneous. You have different elements in each slot, but they are fully typed. They're not tuples. You can increase them, you can shrink them, you can append to them. So they behave like lists, but they are fully typed. And well, balanced trees are another example of something that may or may not be useful in day-to-day programming. Modular arithmetic is something that I struggle with in other languages because, well, for something I do, it would be cool to have this in more low-level languages because you do not have to figure out whether you're using the right moduli, but the compiler can track this for you, and there are applications of this.
Thanks.
So I think the time is over by that counter. So if you have any more... I have 2 minutes, so that counter lies. So are there any more questions? Okay, can you launch the orange box there?
Hey, it's kind of a follow-up question on the one Mario made. Since you talked about shapeless, do you actually use any feature of shapeless specifically in production, or would you recommend it anyway?
Well, I've not used shapeless a lot lately. In fact, I have not used Scala a lot lately because I'm just doing stuff that has to interface with C. So in a sense, no. But if I was using Scala in this period, well, why not? For instance, spry defines the directive in terms of heterogeneous lists. So each spry directive is something that can process a request and a response, and you can chain them in each list of directives. And this is sort of the way that spray accumulates various operations to respond to an HTTP request and give an HTTP response. So in a way that, they get a nice DSL with nice combinators, but everything is fully typed. So this is a very nice application. And, well, I used not to use shapeless much until a few times ago because it looked a little mysterious. Then I prepared this talk, and now that I better understand how it works behind the scenes, well, why not? They're useful.
Thank you.
Okay. So there's a coffee break outside.